Guys, we are going to get into cell potential. Basically, at this point, what we've determined is how to create an electrochemical cell. When we do that, we are considering that there is an anode and a cathode where we have oxidation and reduction taking place. Now, we're going to see what happens when we combine the two sides. That is the idea of cell potential. So, beginning, we're going to look right here at electromotive force, also known as the E cell or cell potential. Cell potential is our voltage that we measure across two sides of the battery, essentially. So you've got your, again, anode and your cathode. When they're connected with a wire, we have a complete circuit, and the difference in reduction potential is what is going to cause a flow of electrons to go from one side to the other. We measure this with a high resistance voltmeter, and this is the equation that we can use in order to determine the cell potential. We look at the reduction potential of the chemical being reduced and subtract away the reduction potential of the chemical that is being oxidized. So by doing this, in reality, what we're doing is considering a combination of two potentials. This negative here, if you were to think about it this way, it also could be thought of as the reduction potential of the thing being reduced being added to the oxidation potential. Okay, so there's two alternate ways of looking at the same concept. It's far simpler for us just to use reduction potentials all the time, which is why we have it set up this way, so you don't really have to think too hard about it. These are reversible reactions. You got to pay attention to that also. So when you think about that, they're going to be subject to Le Chatelier's principle, and we're going to have shifts from the left to the right side as this cell is operating. What we're going to have to do is we're going to have to consider that if I want to compare zinc to copper, or if I want to compare magnesium to copper, then I have to be looking at those two cells under the same set of conditions. So we have a set of standardized conditions that we need to employ. Our standard conditions are going to exist based upon a hydrogen electrode paired up with any other substance. So a hydrogen electrode attached to itself wouldn't have any flow of electrons, so we have a value of 0 volts when you put that together. Putting it with someone else, we're going to get a voltage reading that comes out. Notice one thing here, that this E gets a degree sign, if you will. Sometimes it's shown as a theta, but that indicates that it's under standard conditions. Those conditions that are standard that we always need to be aware of are a temperature of 25 degrees, 298 Kelvin. Gases need to be at 1 atmosphere of pressure when we're using gases. And then if we have an aqueous solution, that solution should be at 1 molar concentration. So take a peek here, and we have this diagram, and it's illustrating our standard hydrogen electrode. So we have our half cell on the right. It could be anything, again, magnesium, lithium, whatever. And then on the left side, we have our hydrogen gas half cell. So it's really challenging. It's really difficult to accurately get this value. Some of the challenges that we find are just setting up the hydrogen to be 1 atmosphere of pressure. Okay? As more hydrogen gas is created, or as hydrogen gas is being taken away, it's hard to equalize that pressure value because the amount of gas is constantly shifting. Also, it's a glass tube with a platinum wire inserted through it, so it's fragile and it's not easy to move around. It breaks very easily. And then the other idea is that our equilibrium that is being established, sometimes it takes a long time to get there. So it's especially important for us to have our standard values of comparison so that we can make predictions without having to experimentally do this every single time. What I want you to do now is based upon your understanding of this equation, right? Remember, it's the cell potential, either E standard or E cell, is equal to the reduction potential of the reduced species minus the reduction potential of the oxidized species. So keep that up there just as a reference point. A cell formed from a silver standard electrode and a hydrogen standard electrode generates a voltage of positive 0.80 volts. Okay, so this is telling us that the E theta, or this standardized cell potential, is positive 80 volts. That's the combination of the two sides. Hydrogen is the more negative electrode and has a value of 0.0 volts. So when you look at this, what we're seeing here is hydrogen is the more negative. That means it is going to be the side that is being oxidized. Hydrogen is more negative, it is oxidized. And that means that our other side, which is our silver, is going to be reduced. That's our cathode. Okay, this is reduced. The first question that we have is we need to write a cell diagram. We need to look at the situation, think of a cell diagram, and calculate our standard potential of that silver electrode, so the reduction potential of the silver. That means I'm looking for this guy, the reduction potential of the reduced thing. I should know the overall cell potential, that's the voltage there, and I should know the anode's cell potential. As I put my cell diagram together, again, it helps to kind of visualize what's taking place here. On the oxidized side, we're going to have our silver, so that's going to be a standard electrode with a piece of metal. That's our silver. And there should be silver ions in that solution. On the other side, we're going to have our hydrogen electrode. So when I connect that, it has to have that platinum rod connecting downwards. And then again, we always include that U-tube, the salt bridge that holds the two sides together. So when I think about this again, it's hydrogen gas with hydrogen ions, silver the metal with silver ions. We've identified that the thing being oxidized is going to be our hydrogen, and the thing being reduced is going to be the silver. So we always write out a cell diagram in order. The thing that is reduced goes last. The thing that is oxidized will always come first. So it's going to be the hydrogen being oxidized. That's the H2. That hydrogen gas is going to turn into hydrogen ions. So I have my H plus in its aqueous form there. So something that we're going to have to consider is that going from a gas to an aqueous, there's no place for our electrons to collect. We're going to have to put in a platinum electrode as a place for those electrons to collect. Well, now that I have that half cell written, I'm going to put in my salt bridge. Then we're going to go ahead and look at our reduction, our cathode. The silver is being reduced, so that tells me that it's the silver ion, Ag+, that's in solution. That is the part that we're going to be reducing. So Ag aqueous is going to turn into the solid form, and that would be our completed cell diagram. Now our next question, part B. It's the same scenario, but we're being asked when a silver electrode is combined with a standard aluminum electrode this time, aluminum, the voltage is measured at positive 2.46 volts, and the aluminum is the more negative electrode. Write the cell diagram and calculate the standard electrode potential of aluminum electrode. I'm realizing that I didn't calculate the cell potential on this last problem. We're going to go back to part A. To calculate out our cell potential, we're going to plug in the numbers that we do know. What we've got is our 0.80 is our cell potential. Our reduced species is the silver, that's our unknown, so we'll just plug that one in there. And then our oxidized species is the hydrogen, and we know that hydrogen is going to be a 0 volt. So when I work this out, I'm going to see that positive 80 volts, Ag and 0 volts, well, by subtracting away the 0, I find that silver must have positive 80 as its individual reduction potential. All right, now we'll do B. So we're looking at aluminum now along with silver, aluminum and silver. The voltage of our cell is positive 2.46 volts, and aluminum is the more negative electrode. Remember, the more negative electrode is where we have oxidation. That's where we have a buildup of electrons. So write a cell diagram and calculate the standard electrode potential for this aluminum electrode. So now, once again, we're going to put together our cell diagram. Since we're talking about oxidation happening in aluminum, we would begin with aluminum as a solid. It's going to turn into the aluminum 3+ ion in solution. We'll write in our salt bridge as usual. And now that I have my salt bridge, we are going to put the cathode in. So this is where reduction occurs. Again, it's aluminum. So we have, or not aluminum, that's already happened. It's the silver, sorry. Silver ions in solution are going to be reduced to silver solid. We don't need platinum in this case because we have metal plates on both sides where we can have a collection of electrons. To figure out our cell potential, remember, this is the anode on the left and the cathode here on the right. Oxidation occurs in the anode, reduction occurs in the cathode. So when I use my equation, the standard cell potential is the reduction potential of the thing being reduced minus the reduction potential of the thing being oxidized. I plug in the things that I know and I solve for the things that I don't. Positive 2.46 is the overall voltage of the cell. It's equivalent to the reduced species, that's going to be our silver, and we know that is going to be a positive 80. 80, sorry. Then I have my unknown, and that's going to be the aluminum. In order to solve for aluminum then, we're going to subtract the 80, and we're going to get a positive 1.66 volts should be equivalent to a negative value for aluminum. So if I want to get a positive aluminum value, I'm going to have to multiply both sides by -1. Aluminum has a standard reduction potential of negative 1.66 volts. Okay? So now let's go on to question C. If the beaker containing aluminum ions has distilled water added to it, what would happen to the voltage of our cell? So we've got to consider what's happening on both sides. Remember, Le Chatelier's principle, it applies here, and we've got to consider what's happening with the voltage. So I'm going to consider both sides of this. We have our anode where the oxidation occurs. We have our cathode where the reduction occurs. On the anode side, we established that the aluminum is being oxidized and the silver is being reduced. So here are our relevant equations. The silver is gaining an electron to become the solid silver. The aluminum solid is going to be turning into aluminum 3+ and giving 3 electrons away. So, question is, if these are equilibria, double arrows, what happens when I add distilled water to the aluminum side? Well, adding water is going to cause our molarity to go down. So the concentration of the aluminum ion is going to decrease. What's going to happen is this creates a void on the product side. It's going to force more of the solid to react to form more of the ions. And in the process, it's going to generate more electrons, more negative charge. This has the effect of creating a larger difference of charge between the negative and the positive electrode. If there's a bigger difference in charge on the negative and positive electrode, this will increase the voltage of the cell. So our end result is we have an increase in the voltage of the cell because we have a larger charge difference between our two plates. Larger charge difference. Okay? Well, that's all we have for today, guys. Hopefully that was informative. I've got some more practice problems that I'll have you be working on, and I will see you again next class.